Welcome. Today's topic is elementary particle. Elementary particle. In particle physics, as elementary particle or fundamental particle is a subparticle with no substructure, has not composed of other particle. Matter in the universe is made up of molecules and hence of atom. After studying structure of nucleus, one might think that perhaps the electrons, protons and neutrons are the building block of the matter universe. But detailed investigation of the cosmic rays, radiation and the study of the nuclear reaction in high energy particle accelerator revealed that there are many more basic particles which are part of the building blocks of the matter in the universe. These particles are called as the elementary particles. Elementary particles are divided into two parts. One is the lepton and second one is the quark. Leptons are available in free form in nature, but quarks are not available in free form. This present in nature in the form of group because of its potential. Then again that quark has again two types. One is the meson and second one is the baryon. That baryon is again two types. One is the half spin baryons and second one is the 3/2 spin baryons. Then we discuss one by one. First one is the lepton. In lepton family there are different elements present. First one is the electron denoted by E bar. Second one is the muon denoted by mu bar, and third one is the tau denoted by tau bar and its antiparticles. Then second one is the meson. In meson there is different particles are present. First one is the pion. In pion family, pi plus, pi node and pi minus. Kaon. In kaon family, k plus and k minus and its antiparticles, k node and k node bar, and eta denoted by eta node. Then third one is the baryons. In baryons, first of all we discuss the half spin baryon. In half spin baryon family, number of particles present. First one is the proton denoted by letter P. Second one neutron, N, lambda, lambda naught and sigma. In sigma family, sigma plus, sigma minus and sigma naught. Next one is the psi, also called as the cascade, cascade naught and cascade minus. 3/2 spin baryon. In 3/2 spin baryon, in that group delta, in delta family, del double plus, del naught and del minus. Next one is the sigma. In sigma family, sigma star plus, sigma star naught and sigma star minus. Next one is the psi, also called as the cascade, cascade star naught and cascade star minus and omega minus. After that we discuss the how to calculate the third component of isospin and strangeness of that elementary particle. First of all we discuss the isospin. How to calculate the isospin I of that elementary particle using that multiplicity formula, capital M is equal to 2i plus 1. Rearrange this formula and isospin I is equal to M minus 1 divided by 2. Using that formula we easily calculate the isospin of each and every particle of the elementary particle, where M is the multiplicity and I is the isospin. Second one is the third component of isospin denoted by letter I3. Using this formula I3 is equal to Q minus Q bar, we easily calculate the all third component of all elementary particles, where here in this formula I3 is the third component of isospin, Q is equal to charge of each particle, and Q bar is the total average charge of group. Then third component is the strangeness. Using Zelman-Nisizima formula, Q is equal to I3 plus B plus S divided by 2. Using that Zelman-Nisizima formula, we calculate the strangeness of each and every particle. Rearrange this formula, then strangeness S is equal to 2 in bracket Q minus I3 bracket complete minus B, where Q is equal to charge, B is the baryon, and I3 is the third component of isospin. Here, using that multiplicity formula, we calculate the isospin. I3 is equal to Q minus Q bar. We calculate the third component of isospin and strangeness of each and every particle of the elementary particle. Then, using that formula, we see that in this table we calculate the here 6 component charge of each particle: lepton, baryon, isospin, third component of isospin, and strangeness. Here, look here, only 5 particle is the strangeness particle: kaon, lambda, sigma, cascade, and omega. These 5 particles are the strangeness particle. In problem, we use, if in reaction there is a lepton present, then use the +1. If anti-lepton present, then use the -1, and other particle, then use the 0. Similarly, in meson, in reaction, in suppose meson particles are present, then use the +1. If anti-meson are present, then use the -1, and other particles, then use the 0. Next one is baryon. If in reaction baryons are present, then use the +1. Antibaryons are present, then use -1, and other, then use the 0. Type of reaction. In elementary particle, there are number of types of reaction. First one is the strong reaction. How to decide the given reaction is a strong reaction? If in given reaction RHS side 2 strange particles, then this reaction is called as the strong reaction. Second one is the weak reaction. That weak reaction is divided into 3 types. First one is the leptonic, second one is the semi-leptonic, and third one is the hadronic. How to decide reaction is leptonic? In reaction, all particles are leptons only, then this reaction is called as the leptonic. Second one is semi-leptonic. In given reaction, particles are lepton as well as quarks or baryons, then this reaction are called as the semi-leptonic. And in reaction, only no leptons are present, and this reaction is called as the hadronic. And third one is the electromagnetic reaction. If in given reaction photons are present, then that reaction is called as the electromagnetic reaction. In elementary particles, there are 3 types of reaction: strong reaction, weak reaction. That weak reaction, again 3 types: leptonic, semi-leptonic, hadronic, and third one is the electromagnetic reaction. How to decide the reaction is allowed or forbidden? Okay, then use the different selection rule, that after decide that reaction is strong or weak, and in weak, semi-leptonic, leptonic, or hadronic or electromagnetic reaction. After decide that reaction, we decide that given reaction is allowed or forbidden. Using this, we use the selection rule. If reaction is strong reaction, then we decide given reaction is a strong reaction. After that, we use that selection rule. Del Q is equal to 0, del L is equal to 0, del B is equal to 0, del I is equal to 0, del I3 is equal to 0, and del S is equal to 0. If all are conserved, then given reaction is allowed, otherwise forbidden. Second one is weak reaction. In weak reaction, first leptonic. In leptonic, use the selection rule: del Q is equal to 0 and del L is equal to 0. In that selection rule, that del Q is equal to 0 and del L is equal to 0 are conserved, then given reaction are allowed or otherwise forbidden. In semi-leptonic, we use the selection rule. Del Q is equal to 0, del L is equal to 0, del B is equal to 0 and del S is equal to plus or minus 1. If all are conserved, then given reaction is allowed, otherwise forbidden. Hadronic. In hadronic reaction, we use the selection rule. Del Q is equal to 0, del B is equal to 0, del S is equal to plus or minus 1. All are conserved, then given reaction is allowed, otherwise forbidden. In electromagnetic reaction, use the selection rule. Del Q is equal to 0, del L is equal to 0, del B is equal to 0, del I3 is equal to 0, del S is equal to 0. Here only del I is not equal to 0. In first strong reaction and in electromagnetic reaction only differ that here del I is not equal to 0. If all are conserved, then given reaction is allowed, otherwise forbidden. This is very important topic in CSIR exam. Many times here asking the question, decide following reaction is allowed or forbidden. That 5 marks question in CSIR NET exam. Then we problem number first, decide the following reaction is allowed or forbidden. That reaction is K minus, then this is reactants and products is pi plus pi minus plus E minus plus neutrino of U. This is the anti-neutrino of lepton. Then solution of that. The see that reaction. In that reaction, here RHS side is the meson and here meson plus leptons. That's why mix lepton plus hadrons. That's why this reaction is called as semi-leptonic reaction. In semi-leptonic reaction, selection rule is del Q is equal to 0, del L is equal to 0, del B is equal to 0 and del S is plus or minus 1. First of all, del Q, charge, reactants and products is equal to 0. This is conserved. Then second one is del L, lepton. Here 0, reactants and product side. Here also 0. That means that del L is also conserved. Then del B, baryon in LHS and in RHS. No baryons are present. That's why del B also conserved. And del S, here K is the strainless particle. That's product side no strainless particle, then del S is equal to minus 1. That means this reaction is follow that selection rule. Del Q is equal to 0, del L is equal to 0, del B is equal to 0 and del S is equal to minus 1. Then this reaction is allowed. Because of this reaction is follow that selection rule, all are conserved, then this reaction is called as the allowed reaction. Thank you very much.